Learning objectives. In this chapter, the user would learn the following in detail: Transmission Control Protocol (TCP) and User Datagram Protocol (UDP), TCP connection establishment, TCP flow control, TCP congestion control, Jacobson's and Kahn's algorithm, window management, TCP extensions, remote procedure call RPC, bulk transfer blast. Bulk transfer blast. Unlike AAL and IP, bulk transfer tries to recover from lost fragments. Strategy: selective retransmission, partial acknowledgements, also known as selective acknowledgements. Blast details. Sender: after sending all fragments, set timer done. If receive SRR, send missing fragments and reset done. If timer done expires, free fragments. Receiver: when first fragments arrives, set timer last _ frag. When all fragments present, reassemble and pass up. 4 exceptional conditions. If last fragment arrives but message not complete, send SRR and set timer retry. If timer last frag expires, send SRR and set timer retry. If timer retry expires for first or second time, send SRR and set timer retry. If timer retry expires a third time, give up and free partial message. Blast header format. MID must protect against wraparound. Type is equal to data or SRR. Num frags indicates number of fragments. Frag mask distinguishes among fragments. If type is equal to data, identifies this fragment. If type is equal to SRR, identifies missing fragments. Remote procedure call. One common pattern of communication used by application programs is the request-reply paradigm, also called message transaction. A client sends a request message to a server and the server responds with a reply message, with the client blocking, suspending execution to wait for the reply. A transport protocol that supports the request-reply paradigm is much more than a UDP message going in one direction followed by a UDP message going in the other direction. It needs to deal with correctly identifying processes on remote hosts and correlating requests with responses. This section describes another category of transport protocol called Remote Procedure Call (RPC) that more closely matches the needs of an application involved in a request-reply message exchange. RPC fundamentals. RPC is actually more than just a protocol. It is a popular mechanism for structuring distributed systems. RPC is popular because it is based on the semantic of a local procedure call. The application program makes a call into a procedure without regard for whether it is local or remote and blocks until the call returns. When the procedures being called are actually methods of remote objects in an object-oriented language, RPC is known as Remote Method Invocation (RMI). While the RPC concept is simple, there are two main problems that make it more complicated than local procedure calls. The network between the calling process and the called process has much more complex properties than the backplane of a computer. For example, it is likely to limit message sizes and has a tendency to lose and reorder messages. The computers on which the calling and called processes run may have significantly different architectures and data representation formats. Thus, a complete RPC mechanism actually involves two major components: a protocol that manages the messages sent between the client and server processes and that deals with the potentially undesirable properties of the underlying network. Programming language and compiler support to package the arguments into a request message on the client machine and then to translate this message back into the arguments on the server machine and likewise with the return value. This piece of the RPC mechanism is usually called a stub compiler. What happens when a client invokes a remote procedure? First, the client calls a local stub for the procedure, passing it the arguments required by the procedure. This stub hides the fact that the procedure is remote by translating the arguments into a request message and then invoking an RPC protocol to send the request message to the server machine. At the server, the RPC protocol delivers the request message to the server stub, sometimes called a skeleton, which translates it into the arguments to the procedure and then calls the local procedure. After the server procedure is complete, it returns the answer to the server stub, which packages this return value in a reply message that it hands off to the RPC protocol for transmission back to the client. The RPC protocol on the client passes this message up to the client stub, which translates it into a return value that it returns to the client program. Identifiers in RPC. Two functions that must be performed by any RPC protocol are: provide a namespace for uniquely identifying the procedure to be called, match each reply message to the corresponding request message. Provide a namespace for uniquely identifying the procedure to be called. A flat namespace would simply assign a unique unstructured identifier to each procedure, and this number would be carried in a single field in an RPC request message. This would require some kind of central coordination to avoid assigning the same procedure number to two different procedures. Alternatively, the protocol could implement a hierarchical namespace analogous to that used for file path names, which requires only that a file's base name be unique within its directory. This approach potentially simplifies the job of ensuring uniqueness of procedure names. A hierarchical namespace for RPC could be implemented by defining a set of fields in the request message format, one for each level of naming in, say, a 2 or 3 level hierarchical namespace. Match each reply message to the corresponding request message. The key to matching a reply message to the corresponding request is to uniquely identify request replies pairs using a message ID field. A reply message had its message ID field set to the same value as the request message. When the client RPC module receives the reply, it uses the message ID to search for the corresponding outstanding request. To make the RPC transaction appear like a local procedure call to the caller is blocked, example, by using a semaphore until the reply message is received. When the reply is received, the blocked caller is identified based on the request number in the reply. The remote procedure's return value is obtained from the reply and the caller is unblocked so that it can return with that return value. Challenge in RPC. One of the recurrent challenges in RPC is dealing with unexpected responses, and we see this with message IDs. One way to eliminate this problem is to use a boot ID. A machine's boot ID is a number that is incremented each time the machine reboots. This number is read from disk, incremented, and written back to disk during the machine startup procedure. This number is then put in every message sent by the host. If a message is received with an old message ID but a new boot ID, it is recognized as new message. In effect, the message ID and boot ID combine to form a unique ID for each transaction. Overcoming network limitations. RPC protocols often perform additional functions to deal with the fact that networks are not perfect channels. Two such functions are provide reliable message delivery, support large message sizes through fragmentation and reassembly. An RPC protocol can implement reliability using acknowledgements and timeouts similar to TCP. The client sends a request message and the server acknowledges it. After executing the procedure, the server sends a reply message and the client acknowledges the reply. Either a message carrying data or the ACK sent to acknowledge that message may be lost in the network. To account for this possibility, both client and server save a copy of each message they send until an ACK for it has arrived. Each side also sets a retransmit timer and resends the message should this timer expire. Both sides reset this timer and try again some agreed upon number of times before giving up and freeing the message. If an RPC client receives a reply message, the corresponding request message must have been received by the server. Hence, the reply message itself is an implicit acknowledgement, and any additional acknowledgement from the server is not logically necessary. Assuming the protocol makes request-reply transactions sequentially, one transaction must complete before the next begins. Above sequence would severely limit RPC performance. Hence, RPC protocols implement a channel abstraction. Within a given channel, request-reply transactions are sequential. There can only be one transaction active on a given channel at any given time, but there can be multiple channels. Each message includes a channel ID field to indicate which channel the message belongs to. A request message in a given channel would implicitly acknowledge the previous reply in that channel if it hadn't already been acknowledged. An application program can open multiple channels to a server if it wants to have more than one request-reply transaction between them at the same time. The application would need multiple threads. The reply message serves to acknowledge the request message, and the subsequent request acknowledges the preceding reply. A server may crash before generating the reply. To help the client distinguish between a slow server and a dead server, the RPC's client side periodically sends an "Are you alive?" message to the server, and the server side responds with an ACK. Alternatively, the server could send "I am still alive" messages to the client without the client having first solicited them. The client-initiated approach is more scalable because it puts more of the per-client burden managing the timer on the clients. RPC reliability may include the property known as at most once semantics. This means that for every request message that the client sends, at most one copy of that message is delivered to the server each time the client calls a remote procedure. That procedure is invoked at most one time on the server machine. To implement at most one semantics, RPC must maintain some state information that identifies past requests. One approach is to identify requests using sequence numbers, so a server need only remember the most recent sequence number. Unfortunately, this would limit an RPC to one outstanding request to a given server at a time, since one request must be completed before the request with the next sequence number can be transmitted. Channels provide a solution. The server could recognize duplicate requests by remembering the current sequence number for each channel without limiting the client to one request at a time. Some support a semantics that is facetiously called zero or more semantics. That is, each invocation on a client results in the remote procedure being invoked zero or more times. If the remote procedure being invoked is idempotent, multiple invocations have the same effect as just one. Then the RPC mechanism need not support at most one semantics. A simpler, possibly faster implementation will suffice. The two reasons why an RPC protocol might implement message fragmentation and reassembly are: it is not provided by the underlying protocol stack. It can be implemented more efficiently by the RPC protocol. Synchronous versus asynchronous protocols. One way to characterize a protocol is by whether it is synchronous or asynchronous. At the asynchronous end of the spectrum, the application knows absolutely nothing when sending returns. It not only doesn't know if the message was received by its peers, but it doesn't even know for sure that the message has successfully left the local machine. At the synchronous end of the spectrum, the send operation typically returns a reply message. That is, the application not only knows that the message it sent was received by its peer, but it knows that the peer has returned an answer. Thus, synchronous protocols implement the request-reply abstraction, while asynchronous protocols are used if the sender wants to be able to transmit many messages without having to wait for a response. RPC protocols are synchronous protocols. RPC implementation: Sun RPC DCE. Sun RPC, a widely used RPC protocol also known as ONC RPC, Open Network Computing RPC. DCE RPC is part of the Distributed Computing Environment DCE. DCE is a set of standards and software for building distributed systems that was defined by the Open Software Foundation (OSF), a consortium of computer companies. Sun RPC. Sun RPC became a de facto standard thanks to its wide distribution with Sun workstations and to the central role it plays in Sun's popular network file system NFS. The IETF subsequently adopted it as a standard Internet protocol under the name ONC RPC. Sun RPC uses two-tier identifiers to identify remote procedures: a 32-bit program number and a 32-bit procedure number. The program number and procedure number are transmitted in the Sun RPC request messages header. A Sun RPC request represents a request to call the specified program and procedure on the particular machine to which the request was sent, even though the same program number may be implemented on other machines in the same network. Thus, the address of the server's machine, example an IP address, is an implicit third tier of the RPC address. Different program numbers may belong to different servers on the same machine. These different servers have different transport layer demux keys, example UDP ports, most of which are not well-known numbers but instead are assigned dynamically. These demux keys are called transport selectors. A well-known address is assigned to one program on the remote machine, and that program handles the task of telling clients which transport selector to use to reach any other program on the machine. The original version of this Sun RPC program is called the port mapper, and it supports only UDP and TCP as underlying protocols. RPC bind, which evolved from the port mapper, supports arbitrary underlying transport protocols. As each Sun RPC server starts, it calls an RPC bind registration procedure on the server's own home machine to register its transport selector and the program numbers that it supports. A remote client can then call a RCP bind lookup procedure to look up the transport selector for a particular program number. XID. An XID is a unique transaction ID used only by one request and the corresponding reply. After the server has successfully replied to a given request, it does not remember the XID. Because of this, Sun RPC cannot guarantee at most once semantics. The request message contains variable length credentials and verifier fields, both of which are used by the client to authenticate itself to the server, that is, to give evidence that the client has the right to invoke the server. DCE RPC. DCE RPC, like Sun RPC, can be implemented on top of several transport protocols, including UDP and TCP. It defines a two-level addressing scheme. The transport protocol demultiplexes to the correct server. DCE RPC dispatches to a particular procedure exported by that server, and clients consult an endpoint mapping service similar to Sun RPC's port mapper to learn how to reach a particular server. DCE RPC implements at most once call semantics. The client sends a request message. The server eventually replies with a response message, and the client acknowledges ACK the response. Instead of the server acknowledging the request messages, however, the client periodically sends a ping message to the server which responds with a working message to indicate that the remote procedure is still in progress. If the server's reply is received reasonably quick, no pings are sent. The server can respond to a request message with a reject message indicating that a call has been rejected, and it can respond to a ping message with a no call message indicating that the server has never heard of the caller. Each request-reply transaction in DCE RPC takes place in the context of an activity. An activity is a logical request-reply channel between a pair of participants. At any given time, there can only be one message transaction active on a given channel. Like the concurrent logical channel approach, the application programs have to open multiple channels if they want to have more than one request-reply transaction between them at the same time. The activity to which a message belongs is identified by the message's activity ID field. A sequence num field then distinguishes between calls made as part of the same activity. It serves the same purpose as Sun RPC's XID transaction ID field. DCE RPC keeps track of the last sequence number used as part of a particular activity so as to ensure at most once semantics. To distinguish between replies sent before and after a server machine reboots, DCE RPC uses a server boot field to hold the machine's boot ID. DCE RPC supports fragmentation and reassembly in the RPC protocol. If an underlying protocol such as IP provides fragmentation reassembly, a more sophisticated algorithm implemented as part of RPC can result in quicker recovery and reduced bandwidth consumption when fragments are lost. The fragment num field uniquely identifies each fragment that makes up a given request or reply message. Each DCE RPC fragment is assigned a unique fragment number, example 0, 1, 2, 3, and so on. Typical DCE RPC message exchange. Both the client and the server implement a selective acknowledgement mechanism which works as follows. First, each fragment that makes up the request message contains both a unique fragment num and a flag indicating whether this packet is a fragment of a call, frag, or the last fragment of a call, last frag. Request messages that fit in a single packet carry a no frag flag. The server knows it has received the complete request message when it has the last frag packet and there are no gaps in the fragment numbers. Second, in response to each arriving fragment, the server sends a FAQ, fragment acknowledgement, message to the client. This acknowledgement identifies the highest fragment number that the server has successfully received. The server selectively acknowledges any higher fragment numbers it has received out of order. It does so with a bit vector that identifies these out-of-order fragments relative to the highest in-order fragment it has received. Finally, the client responds by retransmitting the missing fragments. Fragmentation with selective acknowledgements. TCP congestion control. Congestion control involves preventing too much data from being injected into the network, thereby causing switches or links to become overloaded. Congestion control is concerned with how hosts and networks interact. Congestion in a network or internet creates problems for the end systems, reduced availability and throughput, and lengthened response times. Within a switched network, such as a packet switching or frame relay network, dynamic routing can be used to alleviate congestion by spreading the load more evenly. Due to the variance in network performance, the retransmission of octets affects TCP congestion. TCP maintains a queue of segments that have been sent but not yet acknowledged. The TCP specification states that TCP will retransmit a segment if it fails to receive an acknowledgement. By dynamically adjusting retransmission time, sending TCP have an impact on network congestion. If a TCP sends data too soon when congestion occurs, the retransmitted data increases the congestion in the network. Dynamic routing can alleviate congestion by spreading load more evenly, but only effective for unbalanced loads and brief surges in traffic. Congestion can also be controlled by limiting amount of data entering the network. RSVP signaling may help but not widely implemented. TCP congestion control is difficult. IP is connectionless and stateless with no provision for detecting or controlling congestion. No cooperated distributed algorithm to bind together various TCP entities. TCP flow and congestion control. The rate at which TCP entity can transmit is determined by rate of incoming ACKs to previous segments with new credit. Rate of ACK arrival determined by round-trip path between source and destination. Bottleneck may be destination or internet, and only the internet bottleneck can be due to congestion. Ideally, returning ACK space the signal in steady state. The sender rate matches the ACK arrival rate, equals to the slowest link on the path. Such regulation of flow is known as TCP self-clocking behavior. However, this is rarely achieved due to fluctuation of queuing delays at the routers and switches. So, using a constant factor for RTO may not be suitable. Need to consider RTT variability. Retransmission timer management. 3 techniques to calculate retransmission timer RTO. RTT variance estimation, exponential RTO backoff, Kahn's algorithm. RTT variance estimation, Jacobson's algorithm. 3 sources of high variance in round-trip time RTT. If data rate relatively low, then transmission delay T will be relatively large, with large variance due to variance in packet size. Load may change abruptly due to other sources. Peer may not acknowledge segments immediately. Introduced a variation measure called mean deviation, as shown. SDEV is a RTT variability factor similar to MDEV, as shown. SRTT, smooth round trip time. Figure Jacobson's RTO calculation. Jacobson's algorithm can significantly improve TCP performance, but exponential RTO backoff algorithm is the RTO to use for retransmitted segments. Kahn's algorithm is the round-trip samples to use as input to Jacobson's algorithm. Kahn's algorithm. Do not use measured RTT of retransmitted segments to update SRTT and SDEV. Calculate backoff RTO when a retransmission occurs. Use backoff RTO for segments until an ACK arrives for a segment that has not been retransmitted. Then Jacobson's algorithm is reactivated to calculate RTO. If an ACK is received for retransmitted segment, there are two possibilities. ACK is for first transmission. ACK is for second transmission. TCP source cannot distinguish these two cases. Window management. In addition to techniques for improving the effectiveness of the retransmission strategy, window management approaches have an effect on congested networks. Besides improving RTO calculation, we need to know how to manage sender window has direct effect on congestion. Important techniques are slow start, dynamic windows sizing on congestion, fast retransmit, fast recovery. Slow start. The larger the send window used in TCP, the more segments that a TCP source can send before it must wait for an acknowledgement. In the ordinary course of events, the nature of TCP paces the operation appropriately. This is that when data is transmitted over slow connections, the send speed adjusts automatically according to the connection. This is called the self-clocking nature of TCP. Slow start operates by observing that the rate at which new packets should be injected into the network is the rate which the acknowledgements are returned by the other end. When a new connection is opened, TCP entity is only allowed to send one segment at a time. Slow start adds another window to the sender's TCP, the congestion windows, called CWND. This congestion window tells how many segments can be sent before wait for ACKs. When a new connection is established with a host on another network, the congestion window is initialized to one segment. The sender starts by transmitting one segment and waiting for its ACK. When that ACK is received, the congestion window is incremented from 1 to 2 and 2 segments can be sent. The congestion window can be expanded by the power of 2 for every successful ACK. In effect, the slow start mechanism probes the internet to make sure that it is not sending too many segments into an already congested environment. As acknowledgements arrive, TCP is able to open up its window until the flow is controlled by the incoming ACKs rather than CWND. At some point, the capacity of the internet can be reached and an intermediate router will start discarding packets. This tells the sender that its congestion window has gotten too large. According to high-speed networks, slow start method has been found to work effectively for initializing a connection. This is true if data is sent on large blocks at a time. If the data is sent as multiple small packets at a time, the slow start scheme in fact slows the operation. This is the case when www pages are viewed on the internet. Most www pages consist of multiple small data packets which are sent one at a time. All graphic objects on a page form an individual file which are sent separately to the viewer. There are two standards versions that can be used when sending the information: HTTP 1.0 and HTTP 1.1. Most HTTP 1.0 implementations send the information one at a time, where for every object the slow start mechanism is used. HTTP 1.1 is able to send the whole set of information once, thus the slow start scheme is used only once. Dynamic window sizing. At some point, either before or after CWND reaches the size of the credit allocated by the other side, a segment is lost. This signals that congestion is occurring. It is not clear how serious the congestion is. But when congestion occurs, TCP must slow down transmission rate of packets into the network. In case congestion occurs, the CWND is set to 1. The network recovers from congestion slowly, and thus the slow start scheme is too rapid on congested network. If the exponential growth of packets were used on congested network, the situation would get worse. Congestion avoidance and slow start require that two variables are maintained for each connection: a connection window CWND and a slow start threshold size SS thresh. The congestion control mechanism has a linear growth compared with slow start's exponential growth. The combined algorithm operates as follows. Initialization for a given connection: set CWND to 1 segment and SS thresh to 65535 bytes. Select the smaller value of the CWND and the receiver's advertised window size. In the optimal send strategy, the sender may send more than the receiver's advertised window size, where the receiver's buffer is expected to be emptied before new data arrives. Thus, the optimal strategy is not allowed to be used. When congestion occurs, indicated by a timeout, set SS thresh is equal to CWND by 2. Set CWND is equal to 1 and perform the slow start process until CWND is equal to SS thresh. In this phase, CWND is increased by 1 for every ACK received. For CWND greater than or equal to SS thresh, increase CWND by 1 for each round trip time. Fast retransmit. When TCP sends a message, it waits for acknowledgements to come back before it can advance its window. The time delay varies between successive transmissions in TCP, and an adaptive method is used in calculating retransmission timer RTO. Smoothed round trip time SRTT is used to calculate estimate round trip time. This value is set somewhat greater than estimated RTO. Jacobsen has proposed two procedures called fast retransmit and fast recovery to improve the performance provided by RTO. Fast retransmit takes advantage of the following rule in TCP. If a TCP entity receives a segment out of order, it must immediately issue an ACK for the last in-order segment that was received. TCP will continue to repeat this ACK with each incoming segment until the missing segment arrives in its buffer. When the hole is plugged, TCP sends a cumulative ACK for all of the in-order segments received so far. Since TCP does not know whether a duplicate ACK is caused by a lost segment or just a reordering of segments, it waits for a small number of duplicate ACKs to be received. It is assumed that if there is just a reordering of the segments, there will only be one or two duplicate ACKs before the reordered segment is processed, which will then generate a new ACK. If 3 or more duplicate ACKs are received in a row, it is a strong indication that a segment has been lost. Fast recovery. When a TCP entity retransmits a segment using fast retransmit, it knows or assumes that a segment was lost. This is even though it has not yet timed out on that segment. Accordingly, the TCP entity should take congestion avoidance measures. This is not the case if ACKs have returned. It indicates that data segments are arriving at the other end rather regularly. In this case, the CWND is cut in half and then is proceeded with linear growth of CWND. This technique avoids the initial exponential slow start process. TCP connection establishment. Connection establishment. A TCP connection begins with a client caller doing an active open to a server callee. Assuming that the server had earlier done a passive open, the two sides engage in an exchange of messages to establish the connection. Only after this connection establishment phase is over do the two sides begin sending data. As soon as a participant is done sending data, it closes one direction of the connection, which causes TCP to initiate a round of connection termination messages. While connection setup is an asymmetric activity, one side does a passive open and the other side does an active open. Connection teardown is symmetric. Each side has to close the connection independently. Therefore, it is possible for one side to have done a close, meaning that it can no longer send data, but for the other side to keep the other half of the bidirectional connection open and to continue sending data. Three-way handshake. The algorithm used by TCP to establish and terminate a connection is called a three-way handshake. The three-way handshake involves the exchange of three messages between the client and the server. The idea is that two parties want to agree on a set of parameters which, in the case of opening a TCP connection, are the starting sequence numbers the two sides plan to use for their respective byte streams. First, the client, the active participant, sends segment to the server, the passive participant, stating the initial sequence number it plans to use. Flags is equal to SYN, sequence num is equal to X. The server then responds with a single segment that both acknowledges the client sequence number. Flags is equal to ACK, ACK is equal to X plus 1, and states its own beginning sequence number. Flags is equal to SYN, sequence num is equal to Y. Both the SYN and ACK bits are set in the flags field of this second message. Finally, the client responds with a third segment that acknowledges the server's sequence number. Flags is equal to ACK, ACK is equal to Y plus 1. The reason that each side acknowledges a sequence number that is one larger than the one sent is that the acknowledgement field actually identifies the next sequence number expected, thereby implicitly acknowledging all earlier sequence numbers. A timer is scheduled for each of the first two segments, and if the expected response is not received, the segment is retransmitted. State transition diagram. A state transition diagram shows the states involved in opening a connection, everything above established, and in closing a connection, everything below established. Everything that goes on while a connection is open, that is, the operation of the sliding window algorithm, is hidden in the established state. Each circle denotes a state that one end of a TCP connection can find itself in. All connections start in the closed state. As the connection progresses, the connection moves from state to state according to the arcs. Each arc is labeled with a tag of the form, event, or action. Thus, if a connection is in the listen state and a SYN segment arrives, that is, a segment with SYN flag set, the connection makes a transition to the SYN_RCVD state and takes the action of replying with an ACK plus SYN segment. Two kinds of events trigger a state transition. A segment arrives from the peer, example, the event on the arc from listen to SYN_RCVD, or the local application process invokes an operation on TCP, example, the active open event on the arc from close to SYN_sent. TCP's state transition diagram effectively defines the semantics of both its peer-to-peer interface and its service interface. The syntax of these two interfaces is given by the segment format and by some application programming interface respectively. At each end of the connection, TCP makes different transitions from state to state. When opening a connection, the server first invokes a passive open operation on TCP, which causes TCP to move to the listen state. At some time later, the client does an active open, which causes its end of the connection to send a SYN segment to the server and to move to the SYN_sent state. When the SYN segment arrives at the server, it moves to the SYN_RCVD state and responds with a SYN plus ACK segment. The arrival of this segment causes the client to move to the established state and to send an ACK back to the server. When this ACK arrives, the server finally moves to the established state. In other words, we have just traced the three-way handshake. There are three things to notice about the connection establishment half of the state transition diagram. First, if the client's ACK to the server is lost, corresponding to the third leg of the three-way handshake, then the connection still functions correctly. This is because the client side is already in the established state, so the local application process can start sending data to the other end. Each of these data segments will have the ACK flag set and the correct value in the acknowledgement field, so the server will move to the established state when the first data segment arrives. This is actually an important point about TCP. Every segment reports what sequence number the sender is expecting to see next, even if this repeats the same sequence number contained in one or more previous segments. Secondly, in the state transition diagram, there is a funny transition out of the listen state whenever the local process invokes a send operation on TCP. That is, it is possible for a passive participant to identify both ends of the connection, that is, itself and the remote participant that it is willing to have connect to it, and then for it to change its mind about waiting for the other side and instead actively establish the connection. To the best of our knowledge, this is a feature of TCP that no application process actually takes advantage of. Finally, the arcs that are not shown in the diagram. Specifically, most of the states that involve sending a segment to the other side also schedule a timeout that eventually causes the segment to be resent if the expected response does not happen. These retransmissions are not depicted in the state transition diagram. If after several tries, the expected response does not arrive, TCP gives up and returns to the closed state. Process of terminating a connection. The application process on both sides of the connection must independently close its half of the connection. If only one side closes the connection, then this means it has no more data to send, but it is still available to receive data from the other side. This complicates the state transition diagram because it must count for the possibility that the two sides invoke the close operator at the same time, as well as the possibility that first one side invokes close and then at some later time the other side invokes close. Thus, on any one side, there are three combinations of transitions that get a connection from the established state to the closed state. This side closes first, established fin_wait_1 to fin_wait_2, time_wait, closed. The other side closes first, established close_wait, last_ack, closed. Both sides close at the same time, established fin_wait_1, closing time_wait, closed. A connection in the time_wait state cannot move to the closed state until it has waited for 2 times the maximum amount of time an IP datagram might live in the internet. The reason for this is that while the local side of the connection has sent an ACK in response to the other side's FIN segment, it does not know that the ACK was successfully delivered. As a consequence, the other side might retransmit its FIN segment, and this second FIN segment might be delayed in the network. If the connection were allowed to move directly to the closed state, then another pair of the application process might come along and open the same connection, and the delayed FIN segment from earlier incarnation of the connection would immediately initiate the termination of the later incarnation of that connection. TCP extensions. The significance of adding TCP extensions as options rather than changing the core of the TCP header is that hosts can still communicate using TCP even if they do not implement the options. The two sides agree that they will use the options during TCP's connection establishment phase. First extension. First extension helps to improve TCP's timeout mechanism. Instead of measuring the RTT using a coarse-grained event, TCP can read the actual system clock when it is about to send a segment and put this time, think of it as a 32-bit timestamp in the segment's header. The receiver then echoes this timestamp back to the sender in its acknowledgement, and the sender subtracts this timestamp from the current time to measure the RTT. The timestamp option provides a convenient place for TCP to store the record of when a segment was transmitted. It stores the time in the segment itself. The endpoints in the connection do not need synchronized clocks, since the timestamp is written and read at the same end of the connection. Second extension. The second extension addresses the problem of TCP's 32-bit sequence num field wrapping around too soon on a high-speed network. Rather than defining a new 64-bit sequence number field, TCP uses the 32-bit timestamp just described to effectively extend the sequence number space. TCP decides whether to accept or reject a segment based on a 64-bit identifier that has the sequence num field in the lower order 32 bits and the timestamp in the higher order 32 bits. Since the timestamp is always increasing, it serves to distinguish between two different incarnations of the same sequence number. The timestamp is being used in this setting only to protect against a wraparound. It is not treated as part of the sequence number for the purpose of ordering or acknowledging data. Third extension. The third extension allows TCP to advertise a large window, thereby allowing it to fill larger delay X bandwidth pipes that are made possible by high-speed networks. This extension involves an option that defines a scaling factor for the advertised window. That is, rather than interpreting the number that appears in the advertised window field as indicating how many bytes the sender is allowed to have unacknowledged, this option allows the two sides of the TCP to agree that the advertised window field counts larger chunks. The window scaling option specifies how many bits each side should left shift the advertised window field before using its content to commute an effective window. Fourth extension. The fourth extension allows TCP to augment its cumulative acknowledgement with selective acknowledgements of any additional segments that have been received but aren't contiguous with all previously received segments. This is the selective acknowledgement or SAC option. When the SAC option is used, the receiver continues to acknowledge segments normally. The meaning of the acknowledgement field does not change, but it also uses optional fields in the header to acknowledge any additional blocks of received data. This allows the sender to retransmit just the segments that are missing according to the selective acknowledgement. Without SAC, there are only two reasonable strategies for a sender. The pessimistic strategy responds to a timeout by retransmitting not just the segment that timed out, but any segments transmitted subsequently. In effect, the pessimistic strategy assumes the worst, that all those segments were lost. The disadvantage of the pessimistic strategy is that it may unnecessarily retransmit segments that were successfully received the first time. The other strategy is the optimistic strategy, which responds to a timeout by retransmitting only the segment that timed out. In effect, the optimistic scenario assumes the rosiest scenario, that only the one segment has been lost. The disadvantage of the optimistic strategy is that it is very slow, unnecessarily when a series of consecutive segments has been lost, as might happen when there is congestion. It is slow because each segment's loss is not discovered until the sender receives an ACK from its retransmission of the previous segment. So it consumes 1 RTT per segment until it has retransmitted all the segments in the lost series. With the SAC option, a better strategy is available to the sender. Retransmit just the segments that fill the gaps between the segments that have been selectively acknowledged. TCP flow control. TCP provides a means for the receiver to govern the amount of data sent by the sender. Computers that send and receive TCP data segments can operate at different data rates because of differences in CPU and network bandwidth. As a result, it is possible for sender to send data at a faster rate than the receiver can handle. TCP implements a flow control mechanism that controls the amount of data sent by the sender. This is achieved by using a sliding window mechanism. The receiver TCP module sends back to the sender an acknowledgement that indicates a range of acceptable sequence numbers beyond the last successfully received segment. This range of acceptable sequence numbers is called a window. The window size reflects the amount of buffer space available for new data at the receiver. If this buffer space size shrinks because the receiver is being overrun, the receiver will send back a smaller window size. In the extreme case, the window size will decrease to very small or 1 octet. This is referred to as the silly window syndrome. Most TCP implementations take special measure to avoid it. The goal of the sliding window mechanism is to keep the channel full of data and to reduce the delays for waiting acknowledgements. A feedback mechanism by which the receiver is able to throttle the sender. Flow control is necessary at the link level before incorporating it into the sliding window protocol. Flow control involves preventing senders from overrunning the capacity of receivers. Flow control is an end-to-end issue. Differs from mechanism used in LLC, HDLC and others. Decouples acknowledgement of received data units from granting permission to send more. TCP's flow control is known as a credit allocation scheme, that is, credit-based, and each transmitted octet has a sequence number. TCP header fields for flow control. Sequence number SN of the first octet byte in a data segment. Acknowledgement ACK, number AN, next octet to receive, if any. Window W. If ACK contains AN is equal to I, W is equal to J, octets through SN is equal to I minus 1 acknowledged, permission is granted to send W is equal to J more octets, that is, from octets I through I plus J minus 1. TCP credit allocation mechanism. As shown in figure, credit allocation is flexible. Suppose last message we issued was AN is equal to I, W is equal to J. To increase credit to K greater than J, when no new data B issues, AN is equal to I, W is equal to K. To acknowledge a segment containing M octets, M less than J, without allocating more credit, B issues AN is equal to I plus M, W is equal to J minus M. Credit policy. Receiver needs a policy for how much credit to give sender. Conservative approach. Grant credit up to limit of available buffer space. May limit throughput in long delay situations. Optimistic approach. Grant credit based on expectation of freeing space before data arrives. Complicating factors. Multiple TCP connections are multiplexed over same network interface, reducing available R and efficiency. For multi-hop connections, D is the sum of delays across each network plus delays at each router. If source data rate R exceeds data rate on one of the hops, that hop will be a bottleneck. Lost segments are retransmitted, reducing throughput. Impact depends on retransmission policy. Retransmission strategy. TCP relies exclusively on positive ACKs and retransmission on ACK timeout. There is no explicit negative ACK. Retransmission required when segment arrives damaged as indicated by checksum error causing receiver to discard segment. Segment fails to arrive, lost. TCP implementation policy options. Send may transmit per batch or buffer limit. Deliver similar as send primitive. Accept in order, discard out of order segments, go back N. In window, accept segments in receive window SR. Retransmit. First only one timer for a queue. Expire. Retransmit front of queue. Batch. One timer for a queue. Expire. Retransmit all in queue. Individual. One timer for each segment. Acknowledge. Immediate. Cumulative. Transmission Control Protocol (TCP). Transmission Control Protocol (TCP) is the most widely used protocol. It is also the most carefully tuned. TCP guarantees the reliable, in-order delivery of a stream of bytes. It is a full duplex protocol, meaning that each TCP connection supports a pair of byte streams, one flowing in each direction. It also includes a flow control mechanism for each of these byte streams that allows the receiver to limit how much data the sender can transmit at a given time. Like UDP, TCP supports a demultiplexing mechanism that allows multiple application programs on any given host to simultaneously carry on a conversation with their peers. TCP implements a highly tuned congestion control mechanism. Flow control involves preventing senders from overrunning the capacity of receivers. Congestion control involves preventing too much data from being injected into the network, thereby causing switches or links to become overloaded. Thus, flow control is an end-to-end issue, while congestion control is concerned with how hosts and networks interact. End-to-end issues. Issue 1. TCP supports logical connections between processes that are running on any two computers in the Internet. TCP needs an explicit connection establishment phase during which the two sides of the connection agree to exchange data with each other. This difference is analogous to having to dial up the other party rather than having a dedicated phone line. TCP also has an explicit connection teardown phase. Issue 2. A single physical link that always connects the same two computers has a fixed RTT. TCP connections are likely to have wildly different round-trip times. The timeout mechanism that triggers retransmissions must be adaptive in the sliding window algorithm. Issue 3. Packets may be reordered as they cross the Internet, but this is not possible on a point-to-point link where the first packet put into one end of the link must be the first to appear at the other end. Packets that are slightly out of order do not cause a problem since the sliding window algorithm can reorder packets correctly using the sequence number. IP throws packets away after the IP's TTL, time to live, expires. Hence, TCP assumes that each packet has a maximum lifetime. The exact lifetime is known as the maximum segment lifetime (MSL). Issue 4. Any kind of computer can be connected to the Internet, making the amount of resources dedicated to any one TCP connection highly variable, especially considering that any one host can potentially support hundreds of TCP connections at the same time. This means that TCP must include a mechanism that each side uses to learn what resources the other side is able to apply to the connection. This is the flow control issue. Issue 5. The load on the link is visible in the form of a queue of packets at the sender. The sending side of a TCP connection has no idea what links will be traversed to reach the destination. Data being generated by many different sources might be trying to traverse the same slow link. This leads to the problem of network congestion. In TCP, the underlying IP network is assumed to be unreliable and to deliver messages out of order. TCP uses the sliding window algorithm on an end-to-end basis to provide reliable order delivery. If a heterogeneous link is added to one end of the path, then there is no guarantee that this hop will preserve the same service as the other hops. Since the sliding window protocol guarantees that messages are delivered correctly from node A to node B and then from node B to node C, it does not guarantee that node B behaves perfectly. As a consequence of these small windows of vulnerability, it is still necessary to provide true end-to-end checks to guarantee reliable ordered service, even though the lower levels of the system also implement that functionality. The end-to-end argument says that a function should not be provided in the lower levels of the system unless it can be completely and correctly implemented at that level. Therefore, this rule argues in favor of the TCP/IP approach. It allows for functions to be incompletely provided at a low level as a performance optimization. This is why it is perfectly consistent with the end-to-end argument to perform error detection, example CRC, on a hop-by-hop basis. Detecting and retransmitting a single corrupt packet across one hop is preferable to having to retransmit an entire file end-to-end. Segment format. TCP is a byte-oriented protocol, which means that the sender writes bytes into a TCP connection and the receiver reads bytes out of the TCP connection. Although byte stream describes the service TCP offers to application processes, TCP does not itself transmit individual bytes over the internet. Instead, TCP on the source host buffers enough bytes from the sending process to fill a reasonably sized packet and then sends this packet to its peer on the destination host. TCP on the destination host then empties the contents of the packet into a receiver buffer, and the receiving process reads from this buffer at its leisure. A single TCP connection supports byte streams flowing in both directions. The packets exchanged between TCP peers are called segments, since each one carries a segment of the byte stream. Each TCP segment contains the header schematically. The SRC port and DST port fields identify the source and destination ports respectively, just as in UDP. These two fields plus the source and destination IP addresses combine to uniquely identify each TCP connection. TCP's DMUX key is given by the 4-tuple SRC port, SRC IP adder, DST port, DST IP adder. Simplified illustration showing only one direction of the TCP process with data flow in one direction and AC case in the other. The acknowledgement, sequence number, and advertise window fields are all involved in the TCP sliding window algorithm. Since TCP is a byte-oriented protocol, each byte of data has a sequence number. The sequence num field contains the sequence number for the first byte of data carried in that segment. The acknowledgement and advertised window fields carry information about the flow of data going in the other direction. The 6-bit flags field is used to relay control information between TCP peers. The SYN and FIN flags are used when establishing and terminating a TCP connection respectively. The ACK flag is set anytime the acknowledgement field is valid, implying that the receiver should pay attention to it. The URG flag signifies that this segment contains urgent data. When this flag is set, the URG PTR field indicates where the non-urgent data contained in this segment begins. The urgent data is contained at the front of the segment body up to and including a value of URG PTR bytes into the segment. The push flag signifies that the sender invoked the push operation, which indicates to the receiving side of TCP that it should notify the receiving processes of this fact. The reset flag signifies that the receiver has become confused, for example, because it received a segment it did not expect to receive and so wants to abort the connection. The checksum field is used in exactly the same way as for UDP. It is computed over the TCP header, the TCP data, and the pseudo header, which is made up of the source address, destination address, and length fields from the IP header. The checksum is required for TCP in both IPv4 and IPv6. Since the TCP header is of variable length, a HDR-len field is included that gives the length of the header in 32-bit. This field is also known as the offset field, since it measures the offset from the start of the packet to the start of the data. User Datagram Protocol (UDP). User Datagram Protocol (UDP) is an example of a transport protocol. UDP uses processes to indirectly identify each other using an abstract locator, often called a port or mailbox. The basic idea is for source process to send a message to a port and for the destination process to receive the message from a port. The header for an end-to-end protocol that implements this demultiplexing function typically contains an identifier port for both the sender source and the receiver destination of the message. The UDP port field is only 16 bits long. A client process initiates a message exchange with a server process. Once a client has contacted a server, the server knows the client's port and can reply to it. A common approach is for the server to accept messages at a well-known port. That is, each server receives its messages at some fixed port that is widely published. Sometimes, a well-known port is just the starting point for communication. The client and server use the well-known port to agree on some other port that they will use for subsequent communication, leaving the well-known port free for other clients. An alternative strategy is to generalize this idea so that there is only a single well-known port, the one at which the port mapper service accepts messages. A client would send a message to the port mapper's well-known port asking for the port it should use to talk to the whatever service, and the port mapper returns the appropriate port. This strategy makes it easy to change the port associated with different services over time and for each host to use a different port for the same service. When a message arrives, the protocol, example UDP, appends the message to the end of the queue. Should the queue be full, the message is discarded. There is no flow control mechanism that tells the sender to slow down. When an application process wants to receive a message, one is removed from the front of the queue. If the queue is empty, the process blocks until a message becomes available. Finally, although UDP does not implement flow control or reliable ordered delivery, it does a little more work than to simply demultiplex messages to some application process. It also ensures the correctness of the message by the use of checksum. UDP computes its checksum over the UDP header, the contents of the message body, and something called the pseudo header. The pseudo header consists of three fields from the IP header: protocol number, source IP address, destination IP address, plus the UDP length field. The pseudo header is used to verify that this message has been delivered between the correct two endpoints. Conclusion. In this chapter, we have covered the following in detail: Transmission Control Protocol (TCP) and User Datagram Protocol (UDP), TCP Connection Establishment, TCP Flow Control, TCP Congestion Control, Jacobson's and Kahn's algorithm, Window Management, TCP Extensions, Remote Procedure Call (RPC), Bulk Transfer, BLAST.